It's 45 degrees Celsius outside. The sun is beating down, relentless. You're in a city built in a scorching desert, thousands of years ago. No air conditioning, no electric fans. Hell, no electricity at all. Just sand, stone, and the unforgiving sun. You'd expect everyone to be constantly melting, probably suffering from heat stroke, huddled in dark, miserable caves. But here's the mind-bending truth. They weren't ancient civilizations. In Egypt, Mesopotamia, Persia, Rome, didn't just endure the heat, they beat it. They built cities, grand palaces, and everyday homes that were, by all accounts, shockingly comfortable. Sometimes 10, 15, even 20 degrees Celsius cooler inside than the blistering outdoor temperatures. Imagine walking out of a sweltering desert street into a perfectly cool, breezy interior without a single wire, compressor, or refrigerant in sight. How on earth did they pull this off? How did people who couldn't even make ice on demand manage to create living spaces that mimicked the comfort of a modern air-conditioned room? What secret physics did they unlock, then seemingly forget for thousands of years? The answer isn't one simple trick. It's a symphony of incredibly clever, often invisible, engineering principles that turn the very elements working against them, sun, wind, and water, into their greatest allies. Let's start with the most obvious but often underestimated tool, mass. Think about your grandmother's old ceramic casserole dish. It takes a while to heat up, right? But once it's hot, it stays hot. Same with ancient buildings. They weren't built with flimsy plasterboard walls. We're talking about massive, thick structures made of mud, brick, stone, or adobe. Walls that could be a meter, even 2 meters thick. These weren't just for structural integrity. This was thermal mass. During the day, as the sun hammered the exterior, these colossal walls slowly absorbed the heat. It was like a giant, super slow-motion sponge soaking up thermal energy. But because the walls were so thick, that heat took hours, sometimes an entire day, to actually travel through to the interior. So, while it was 40 degrees outside, the inside of the wall was still reflecting the cool of the previous night. By the time the heat finally permeated the wall, it was already evening. The outside temperature had dropped, and now the wall, which was hot on the outside, started radiating its absorbed heat back into the night sky, while the inside slowly began to release its stored coolness. This creates a kind of daily thermal flywheel, always lagging behind the outside temperature, always keeping the interior stable, and much, much cooler. But mass alone won't create a breeze. For that, ancients turned to 2 other natural powerhouses, evaporation and clever air movement. Imagine the iconic Windcatchers, the tall, chimney-like structures you see on ancient Persian and Egyptian buildings. These weren't just decorative. They were sophisticated passive cooling systems, a multi-directional tower, often open, on several sides, designed to literally catch the prevailing breeze, funneling it down into the building. Sometimes, that incoming air was directed over a small pool of water, or even porous ceramic jars filled with water. This is where evaporative cooling kicks in. You know how you feel cooler? When you step out of a shower and the water on your skin starts to evaporate? That's because evaporation is an endothermic process. It draws heat out of its surroundings. As the air passed over water, the water evaporated, taking heat with it, effectively chilling the air before it entered the living space. The result? A cool, moist breeze circulating through the home, sometimes dropping indoor temperatures by a staggering 10 to 15 degrees Celsius below the outside air. That's comparable to what some modern AC units achieve. But what if there was no wind? Or what if you needed even deeper cooling? This is where the truly mind-bending engineering comes in. Enter the Qanat. Originating in ancient Persia, Qanats were elaborate networks of underground tunnels that tapped into distant water tables, bringing fresh water to arid cities. They could stretch for tens of kilometers, dug by hand, sometimes hundreds of feet below the surface. They were incredible feats of hydraulics. But here's the unexpected bonus. Those deep underground tunnels weren't just pathways for water. They were also massive conduits for air. The Earth at those depths stays at a near constant, cool temperature, regardless of the scorching surface. As air traveled through these long, subterranean channels, it cooled down dramatically. Architects learned to tap into these Qanats. They'd build shafts that drew this naturally chilled air from the Qanat directly into homes, public buildings, and even underground ice houses called yakshals, where they could store ice year-round in the middle of the desert. Imagine an entire urban infrastructure designed not just for water supply, but as an enormous natural air conditioning system. The physics here is a combination of thermal mass and the stack effect. Hot air rises. So they'd often have outlets for this cool, Qanat air at ground level, while hot air would naturally exit through higher vents, or windcatchers, creating a constant, gentle circulation of refreshingly cool air. This wasn't just comfort. It was critical infrastructure that allowed civilizations to flourish in climates that should have been uninhabitable. How many modern cities could pull off something like that without a power grid? The Romans, masters of water engineering, took their own approach. Beyond their famous aqueducts and elaborate public baths, they integrated water extensively into their domestic cooling. Wealthy Roman villas often featured internal fountains and shallow pools within courtyards, not just for aesthetics, but for evaporative cooling. Some even had water channeled through pipes embedded within walls, acting like a primitive radiant cooling system. Imagine cool water flowing through your walls, absorbing heat from the room. They weren't afraid to use brute force either. Slaves often operated large, handheld fans, creating localized breezes for the elite. But the widespread use of water and strategically designed architecture meant that, even without active systems, Roman cities were significantly more tolerable than their open, exposed counterparts. The sheer ingenuity makes you wonder, why did we ever abandon these incredible methods? Was it simply the irresistible allure of cheap energy? The convenience of flicking a switch? The knowledge of building these complex, passively cooled structures was passed down through generations, often requiring highly specialized craftsmen. When electricity and mechanical refrigeration arrived, they offered a faster, simpler, though energy-intensive, shortcut. We traded intricate, sustainable systems for brute force technology. Today, as we grapple with soaring energy costs and the undeniable realities of climate change, these ancient solutions are making a dramatic comeback. Modern architects are looking to the past, designing buildings that incorporate thermal mass, passive ventilation, and evaporative cooling. Cities like Masdar and Abu Dhabi, a highly experimental zero-carbon city, are directly inspired by the narrow streets, shaded courtyards, and wind tower concepts of ancient desert architecture. We're rediscovering the wisdom of building with nature, rather than fighting against it. It forces us to ask a crucial question. What if we had continued to evolve these ancient, elegant, energy-free cooling methods instead of abandoning them for energy-hungry electrical systems? Could we build a future that is not only comfortable, but truly sustainable by simply looking back at what our ancestors perfected thousands of years ago? Perhaps the key to our future comfort lies buried, quite literally, in the sand of our past.